Okay, let's get started. Any questions on the problem set? I know there have been a few questions about problem 4, which is the one about memory use. Anything anybody want to raise here? Okay. So we left off with just a little bit left in the Python unit. So let's go back and look at the object-oriented programming in Python. So I just want to do a very brief demo on this, and we can see at least some of the functionality here. So here's an example of creating another one of these indiv classes like we did in R. So we have a little bit of help information here, just like we did for functions when we defined a function that we already saw in our last class. And then any code that you put here is basically code that's going to be executed when the class gets created. So that's sort of relative to the entire class. And then these guys are the specific methods associated with the class that one could use for any given object in that class. So there's a constructor or an initialization function that sort of sets things up when you first create a new instance or instantiation of the class. And then I've just made a couple toy examples of methods that we could call on an object in the class. Questions about that setup? Okay, so I'm going to copy and paste that in. I have a note to myself to do this in Python instead of in IPython, so hopefully that will work. Okay, so you notice it printed out the print statement that I had put in there for the class in general. So we don't yet have any objects in this class. We've just defined the class, and now we can use the class to create objects. I'm not sure why I have this import OOP commented out. Apparently there's an OOP package, but maybe I don't need it. I guess we'll find out. So I'm going to create an object in this class. In this case, I'll create an object for the president, and I'll pass in a name and an age, because those are the things that the initialization function is expecting. And you'll notice all of these functions, all these methods have self as a sort of required argument. And that's basically just referring to the object itself, but from within the code that's managing the object. So here we use self, and we say self.name gets set to whatever the input value of name is. And here, when we want to refer to, say, age and increment it, we say self.age to refer to this object and working with a component of that object. Oops. Okay, so I should be able to do this. It'll say, doesn't, that information is maybe not too helpful, except it does sort of gives me some information at the level of sort of the programming. If I do this, we can see what happens if I don't give it an age. So it says, oh, you're required to give it the second input, that third argument, which is the age of the person. Okay, so that's just the class, and now if I do this, did I already do this? Okay, I already did that. Okay, so we can refer to components of the object with just a dot and then the name of the attribute, or we can refer to one of the methods with a dot and then the name of the method, and we can actually call the method. So I can go ahead and do this. It's going to do the sorts of things that we would expect. And now if I do the get info, it now shows that indeed I have incremented the age. So all of this is actually working as we would expect it to. Any questions about that? So it's pretty straightforward, which is nice and sort of part of the design of it. So you could probably get going pretty quickly with this if you wanted to. It's interesting. I was just looking at this morning that we can actually just add in attributes on the fly. Oops, that's because I didn't put it in quotes. So now I can look at pres.age, but I can also look at pres.vicepres. And there was no vicepres in the actual definition of the class here. In fact, it's interesting that we don't actually even see any explicit definition of what the attributes or fields of the class are. It's sort of just implicit in here that we're passing in these inputs, and then we're assigning them to components of the object. So in some ways, that sort of reminds us a bit of what was going on with the S3 objects in R, but in other ways, the object-oriented programming in Python is somewhat more structured than we saw with the S3 classes. And then if I were to say ask about an attribute that I haven't defined, it's going to say, oh, that attribute doesn't exist. Okay, the other thing that I just want to point out quickly is that, like some of these other objects in Python, if we want to make an actual explicit copy, so we have a separate object in memory, we need to do that explicitly as opposed to just using equals to do an assignment. So if I just used equals, I would have the same effect as we've seen before, that I'm just basically now having a new reference to the same object. And so I need to do this deep copy, which comes from the copy package. So if I do that, that should then work, and then I could modify the new precedent such that wouldn't affect the pres object, which is the older version of the object. Okay, so I think the last thing I'm going to mention about these object-oriented stuff in Python is this, what I think is kind of a neat idea, that you can actually have variables at the level of the class. So what we'll see here is we're going to define a variable called population that you can see is above all the rest of the information in terms of the methods of the class. And then when I refer to population, I'm going to refer to it based on the class name. And what this basically allows me to do is sort of carry along information about the class as a whole that's distinct from any individual member of the class. And so that's, again, is in this idea of modularity, that instead of having some other variable in Python that was sort of keeping track of how many individuals we have in our population, it would be kept track of within the context of this particular class. So that's nice to sort of package that up instead of having a lot of different free-floating objects all around. So here, you'll notice whenever I do an initialization, I increment the size of the population by 1. And then I can refer to the value of that in any, in some other method that I've defined, such as the getInfo, and that should then again give me information about the current value of the population level. So this is going to then look back at the information relative to the class, and that will stay updated. Okay, so I've defined the class. Now I'm going to define 2 people. This is my grad school office mate, so I've decided he's a friend of the president. Okay, so now I've got 2 of these people, and I guess this is probably not going to show us too much because we've already seen what that looks like. The other thing I'll point out here is there are 2 different ways to use the method. We can either just call it in the way that we're used to with the name of the object and then the method, but we could also call it based on the class and pass in the object as the argument. So either one of those will show both the information about Obama and this idea that we now have information about the population, so we can extract that information out. Okay, so I think that's all I want to say about object-oriented stuff in Python. Any questions about that? And any questions about Python in general? This is the end of our whirlwind tour. Okay. I may send out a little poll while you guys are thinking about it, rather than waiting until the end of the semester, and see what you guys thought of whether this was helpful to see this in this brief a form. So if I get a chance to do that, you may see that. Okay, so let's move on to the unit on parallel processing. So the idea is we're going to do a day or 2 on parallel processing, both in general, but actually showing how to do some of the approaches in R. And then we're going to switch to a day or 2 in the next unit 9 will be on dealing with databases and large data sets, and we'll see some methods for working with actual explicit databases, and we'll see some methods for working with big data sets that you couldn't handle in memory. So we're sort of talking about sort of larger kinds of problems, both with the parallel processing in terms of larger sizes of computation, and then with in the data unit with larger sizes of data sets. And of course, those two things could also happen at once. That you've got a lot of processing to do and very large data sets. Okay, so I want to begin just by talking a little bit about computer architecture, because we need to know a little bit about the hardware to then know how to work with it in terms of software. So the sort of core idea here is that up until some number of years ago, with Moore's law, that computer processors were just getting faster and faster and faster, and that increase in speed has tapered off of late. And so instead, the industry has been moving to basically putting more processors in any individual computer. And then the question is, can we take advantage of having those multiple processors to speed up our operations? The problem with that is that instead of just having it all work, you have one computer and it just gets faster and faster and you can just keep your code the same as it always has been, is that if you've now got multiple processors on a given machine, either you or the software behind the scenes has to be smart about splitting up your particular computation to take advantage of those multiple processors. So that's basically the name of the game and what we're going to be talking about here. And in some cases, some of the software that we will use actually does some of this behind the scenes, and we don't need to know too much about what's going on, although it is useful to know basically what's happening. And in other cases, for a given problem that we're creating the code for, we need to actually explicitly go in and figure out how to do the parallelization and break up our job. So that's sort of where things stand. So I'm going to refer. So basically, how do I want to say this? The basic distinction that I want to make here is between what we would call distributed parallel processing and distributed memory parallel processing and shared memory parallel processing. So basically, if you have a single computer, then you're generally going to have memory that's accessible from all of the different processors or cores that are on that machine. And I'm generally going to use processor and core interchangeably. Basically, it's any processing unit on the machine, and those processing units are all going to be able to access that same memory. Once you move to having a computer cluster or a supercomputer, you're then talking about basically having very, very many different computers, which are also often called nodes. Each of those computers or nodes have their own memory, and each of them may indeed have multiple cores or processors on them. But then all of those nodes are then going to have to communicate with each other over some sort of network. So the basic, sort of a pictorial representation of that is that you would have in the distributed memory setup, you basically have a network, hopefully a fast one, and that is connecting the different processors, and each of those has access to their own memory. So you can think of this as what we have, for example, on the SCF. We have a lot of different servers that are all connected by a fast network. Each of them has their own memory. All of the Department of Energy supercomputers, for example, the one up the hill here at Lawrence Berkeley Lab, is also set up in this sort of fashion. Whereas if we're talking about a single computer, such as your laptop or a single desktop, then we basically have a single set of memory, and we have multiple processors. And each of those, via some network, within the machine, is able to access the memory. And so one of the things that we need to realize when we're thinking about breaking up computations is these processors accessing this memory is going to be a lot faster than these processors communicating with each other over this network. So if in general, one of the bottlenecks that will often arise when you're in a situation like this is actually passing the information that you need to pass from one processor to the next. So the more that you can limit the amount of communication that has to go on between any given processor, the better off in general you're going to be in terms of speed of getting your code to run. So there are, for example, there's a line of research in computer science that's basically trying to come up with algorithms that limit the amount of communication. So you have some given task you need to get done. Can I complete this task by splitting up the work across different processors, but in a way where I don't have to pass a lot of information from one processor to another processor? So that's one of the sorts of things that folks in computer science would be looking into. Okay, so I think that sort of summarizes things here. As I said, I'm not going to distinguish much between multiple processors and multiple cores. Basically, we're sort of going to think of those generically as this sort of thing, that you have multiple different computing units. You can call them a processor, you can call them a core, but we're going to want to know how many of them are there on a given computer that we can take advantage of. If you are doing parallel processing in this context, where you have to pass information from one computer or one node to another, one of the protocols that people often use is something called the message passing interface, which is called MPI. So you can write code in C or in Fortran that uses that protocol. There is an R package called RMPI that basically implements that for R, and basically using MPI basically involves doing a bunch of calls that say, pass this chunk of data from this node to that node. Get that chunk of data from this node that was sent to me from that node, that sort of thing. So it's basically sort of the management process of managing when information gets passed from one node to the next and which nodes information is getting passed to and from. We're not really going to talk about that here in the course, but I just wanted to make you guys aware of that. Okay, and then I'm not gonna talk through this, but there are also graphics processing units that you can actually do computations on these things that used to just be used for displaying graphics and doing computer gaming, and also about cloud computing. But basically, the idea here is there's no reason that you can basically set up your own remote virtual computer, with Amazon or Google or one of these companies, or you could set up your own remote virtual cluster, and that these things would operate as if they were actual clusters that had dedicated hardware, like we have in the SCF. Okay, so in terms of different kinds of parallelization, one of the main ways that that jobs get managed once you're working with multiple different cores and managing computations on multiple different processing units is what's called a master-slave paradigm. Basically, that there's one process that's sort of managing the whole thing. That process basically dispatches computations to the different slaves, waits for them to finish, and then collects the information back. So that sort of paradigm is one of the main paradigms that we're going to talk about. And one of the things that can come up in these contexts is you can often get bugs that are really hard to track down, because basically you send off a chunk of processing to get done on one of the cores, and your program just hangs and you never get anything back, and then you have to figure out what's happening on that process, what's happening with that task that you've dispatched. Why is it not sending any information back to me? Is the problem in the communication? Is the problem because the code on the code that's being done in that task failed for some reason and I didn't get an error message passed back to me correctly such that I can interpret it? So this sort of thing tends to happen a lot, and debugging in a parallel context is generally a lot harder than in a serial context. Okay, so one of the basic forms of parallel processing is something called threading. So basically, the idea here is you've got multiple cores on a single machine available to you. So we're in this shared memory context. And basically what happens is whoever's writing the code basically writes the code such that the operating system basically sort of creates these things called threads, which are these things that are seen as sort of quote unquote lightweight processes. And basically the idea is if you did top when you were running threaded code, what you would see is that you would see a processor running, you would see that the machine looks like it's running at more than 100% CPU. And the reason is because, say you saw that it was running at 400% CPU. It's actually using 4 cores, but to the operating system it sort of looks like it's just one process, so that's why it's reporting back as 400% with one job that's running. Whereas we'll see in a little bit that you could also start up 4 explicitly separate processes, and each of them could be running at 100%. So that's sort of one of the ways that we see a distinction between threaded code and code that's explicitly running as multiple processes. So if you wanted to write your own threaded code, you can do that. There's a protocol called OpenMP. It's not too hard. We, for our purposes, will mainly be taking advantage of threading by using linear algebra that's already threaded and that we'll call from R. So that's basically what we're going to do. So as long as you have that the basic linear algebra subroutines, the BLOS, on your system is set up such that R will call a version of the BLOS that uses threading, then anytime you do a linear algebra call, that call will basically distribute the linear algebra calculations across multiple machines. So we've sort of already seen, or you're sort of seeing now in the problem set, an example of this. If I want to multiply matrices, I can think of how I would break up the computations of multiplying rows and columns such that I could break it up such that some of those row-column multiplications get done in one thread, another set of them get done in another thread, another set get done in another thread, and so on and so forth. And there's no reason, if we're doing something as simple as matrix multiplication, that we couldn't break that up, and as long as we keep track of what's going on in the different threads, we then collect that information back and reconstruct the entire matrix that we're trying to compute. So that's basically what goes on behind the scenes when you are using a threaded BLOS. So on the SCF, all of the machines use a threaded BLOS, so that is going on. You don't sort of need to worry about that too much because it'll just happen by default. If you're in some other context, then you would have to investigate to see whether that was set up. But having a threaded BLOS set up either on your own machine or on the system that you're working on is something that could speed up your code quite a bit. And the other thing that I'll mention here, I think I mentioned this before, is even if you don't have a BLOS that is using threading, some BLOS implementations are much faster on a given set of hardware than others are, so you can actually get up to, say, an order of magnitude speed up in your code in some cases if you're really heavily relying on linear algebra by making sure that you are using a fast BLOS. And so some of the ones that are fast, there's something called OpenBLOS. There's something called MKL, which comes from Intel. There's something called ACML, which comes from AMD. So both of these are produced by the chip makers. And then on Apple's, there's something called veclib. So all of these are both fast, and they also allow for threading. However, if you just have a Mac where you didn't do anything to set it up, I don't believe this is implemented by default. So that's just a word of caution there. Okay, so let me just do a quick example, and we'll see this in action on one of the SCF machines. So for the most part, or maybe entirely in this unit, I'm not going to do things through RStudio just because it introduces a little bit more complexity of having to go through the RStudio interface, and it's not totally clear to me sometimes what RStudio is doing in terms of the parallel processing. So I'm just going to do this in R itself, and I'm going to do it on Rwin. All right, so I'm going to start up top. We can see there are a few jobs running on this machine. This is a machine that has 32 separate cores. So we can see that when we look at this, about 6 or so of them are currently being used. You'll actually notice we can see here that what I suspect is going on is this is 2 separate processes that were started up, the ones that the cancer tie, which stands for cancer timing. Those 2 processes were probably started up by the same R job, and where the code got split into 2 separate pieces. And then you'll notice this MJ Wayne job is running at more than 100%, so that's code that's running that is threaded and is using more than one core through this threading mechanism. So let me start up R here. And I'm just going to do a little bit of linear algebra. So what I'm going to do here is I'm going to create a fairly large matrix, and then we're going to time the time it takes to do the operation. I'm I'm going to have an 8,000 by 8,000 matrix X. I'm going to do X transpose X. This is going to produce a positive definite matrix, so basically a covariance matrix. And then what I'm going to do is I'm going to take the Cholesky decomposition of this, so basically a square root matrix, which I've mentioned sort of briefly a couple times, and we're going to see in much more detail in a couple weeks. So this is sort of heavy duty. These are not particularly complicated operations, but they are heavy duty linear algebra, and they're fairly intensive calculations. So particularly with a matrix that size. So we're going to run this in R. So we're just creating our matrix, our 8,000 by 8,000 matrix. If we look here, it looks like we're running at 100% CPU right now, and that's just when I'm doing R norm. So the R norm calculation itself is not threaded. That's just being done as a single operation, as a single task on a single core. But now we're into the linear algebra portion, and you see I'm now running at 800% of CPU. Okay. And it looked like it finished. Okay. So let's try that again. Okay, so it's doing the cross product, and then it's doing the linear algebra. So it's using up around 8 threads or eight cores. And we'll move along. It shouldn't take too long. So here, this was with system.time. You'll notice it gives me both an elapsed time and a user time. And the elapsed time is basically the clock time. The user time is basically the total amount of computing time that it took. And we'll notice that this is about 6 or 7 times as much here, and that reflects the fact that even though in clock time it only took 12 seconds, that was 12 seconds on each of 6 or 7 or 8 different cores that the operation was being done on. So that is consistent, more or less consistent with what we saw with top. Questions so far about anything I've said? Yeah, Alex.
How does your linear algebra computations know how many cores to use? So when you have threads at your disposal,
right.
It's like 28 after 27 after they're being used. So
yeah, so I'm not exactly sure why it seems to be setting it at 8, and I've seen cases where it goes higher than that. So you might see it at 1600% or something even higher. I believe R1 actually has its 32 cores split into 2 separate processing units. And in that case, I believe that it's not going to ever use more than 1600% because it won't use more than 16 cores at a time because those cores are actually split physically on the machine, even though they're accessing the same memory. So in this case, the threading behind the scenes is based on this OpenMP protocol. And the system has a way of basically querying itself. R basically will query, or the BLAS will basically query the system and ask how many cores do you have available for me to use, or how many available in the sense of how much hardware. And it will then set the number of threads that it's going to use based on that. What we're going to see in a second is how we would explicitly set that ourselves. And the other thing that we would notice is if the system were heavily used, so if there were a whole bunch of other people running jobs here, I could run the same code and I might see it running at 200% CPU or 150% CPU because the operating system is trying to manage the fact that multiple tasks from multiple different users are trying to get resources. So there's some degree of the operating system sort of switching back and forth things here. Okay, so now what I'm going to do is I'm going to go in and change how many threads are set up as the maximum number of threads to use for this process. So I'm going to use an environment variable, Unix environment variable called OMP numthreads. So OMP stands for OpenMP, and that's because the BLAS is using this OpenMP protocol. So if you wrote your own C code, you could manage the number of threads by setting this environment variable. But we can also manage the number of threads for the linear algebra for this package that we're calling as well for the BLAS. So I could set this to be, say, 8 or 2 or 4. I'm going to set it to be 1 and force this to basically to be a serial operation. If I want to do that, I need to do that outside of R before I start R, so I need to quit out of R. I can't do this on the fly. And then in Bash, I'm going to set this, I'm going to restart R, and now we'll run this code again. So as before, the R norm should just be taking 100% CPU, so that's no different than before because that's not threaded regardless. And now I'm going to run this, and I should see that this is only at 100%, or sort of working its way up. So here's my job sitting there at 100%. Oh, it keeps moving around. But if you follow it, you'll see that it shouldn't go over 100%. And this will now take presumably 70 some odd seconds, because that was basically the amount of processing time that was recorded last time in total, in aggregate across the different cores. So depending on the system that you're running on, you may need to explicitly set this. If the system administrator doesn't want you using more than 4 cores, you might need to go in and explicitly set this. Or the other thing I'm about to point out is that there are cases where we wouldn't want to use the threaded linear algebra, in which case we would want to set this to 1 to make sure that we weren't doing any threading. And I'll say why in a second. Okay, so while that's moving along, a couple of the reasons why you might not want to use threading. One of them, and maybe I'll skip ahead here, is basically if you're doing a fairly small linear algebra calculation, there's not going to be any advantage in using threading, because basically the overhead in basically setting up the problem and having the computer set up the problem and do the communication and send the jobs off to get done and wait for them to come back is going to be more time than it would take to just do the full thing on 1 core serially. So in that, and sometimes, depending on which version of the BLAS you're using, it may not do a particularly good job of realizing that there's no point in distributing the calculations amongst multiple threads. So you might actually see that it's somewhat slower to run something in a threaded mode than in an unthreaded mode, particularly if you're working with relatively small matrices. So in that case, you might want to explicitly set it to be to only be 1 thread. The other is basically there are some conflicts between different functionality in R and using threading. So one of them is basically that some of the parallel functionality that we're going to see in a little bit basically there's some sort of conflict between that and threading, and the result is basically that your code will just hang and never complete. So the things for which that occurs I've listed up here, and it's basically whenever R tries to do a fork. And what a fork basically is, R is going along, you call fork, it basically calls a system routine called fork, which basically what it does is it takes the code and duplicates it and creates a new identical process. And then both of those processes are then marching along executing the remaining code. So that's a standard method by which you create a new process and get more computations done. The problem is there's some sort of conflict between that and the threading, such that you can't have both the fork processes going and each of them doing threading. Otherwise, if you try and do that, you'll see that they just hang. So that would be a case where you'd want to set OMP num threads to 1. Another is that for some reason our prof is not set up to handle threading, and so you will also see code hang if you try and do rprof with threaded linear algebra. So in either of those cases, you would need to set OMP num threads. So let's go back to R, see if it completed. Okay, so it looks like it completed. Now we see that the elapsed time and the user time are basically the same, indicating that this is code that has been running serially. And it's sort of interesting. It looks like, in this case, the user time, remember from before, I think it was 77 seconds, and now it's 74 seconds. So in total, in aggregate, it's a little bit quicker to just do it serially, and this presumably reflects the fact that there's just some overhead involved in dispatching the different threads and collecting back the information and that sort of thing. In this case, the overhead is pretty minimal, but in other problems, you might see that the overhead grows in relation to the amount of computation that you're getting done. Okay, any questions at this point? Yeah.
You used a command to use only one processor.
Yep.
How would you reverse that and say, okay, now you can use as many as you want?
Yeah, so basically I'd need to do the reverse of what I just did. I would need to exit out of R. And then I would need to go in and set this to be whatever number I wanted. So suppose I wanted to use 4. I saw that it was using 8. For some reason, I didn't think that that was more than I wanted to use for some reason. Either because I thought there was not much efficiency gained in going all the way up to 8, I might as well just use 4, or because on the system, it was better to share resources with other folks using the system, and for that reason I wanted to use 4. So I could do that, and then start R, and then and then move along.
Could you set it equal to like 32 or?
Yeah, I mean, that's interesting. Let's actually try this question of setting it equal to 16. I think for the reason I mentioned before about the cores being separated in two pieces, I don't think 32 will work, but I am sort of curious whether 16 will work. So let's actually go ahead and see what happens. The other thing, this is sort of a good opportunity to also point out this another point I wanted to make, which is oftentimes when you're trying to set up parallel code, you'll notice that basically that you'll see diminishing returns to scale. That even if you had a machine that had, say, 64 cores or 128 cores, and you tried to do the threaded linear algebra with that many cores, you would see that you weren't getting the same speed up relative to the number of cores that you were getting from going from 1 core to 2 cores to 4 cores. So that maybe going from 1 core to 2 cores, you see almost twofold speed up. But then in going from 1 core to 4 cores, you don't see 4 times speed up. You only see 3.5 times speed up. So in general, what you would see is that, okay, so it looks like it probably didn't use, I guess I didn't look at top, but we can see just from what happened in the elapsed time that it doesn't look like it was really taking advantage of those 16 cores, even though I said that it should be able to use 16 threads. So a good rule of thumb when you're writing, well, not maybe after, I guess after you write it. So you've written your code such that it can use threading in some ways, perhaps just behind the scenes by using the threaded linear algebra in R. A good approach to then take as you're trying to run your code is to try and see how it scales with the number of cores. So run it serially, run it with 2 cores, run it with 4 cores, run it with 8 cores. And oftentimes what you'll see, if you just sort of make a plot of it, is this idea, this notion that there's a diminishing return to the number of cores that you've used. And so, suppose you have 1, 2, 4, 8, and this is the amount of time it took with 1. You might see that it does something like this. And at that point, once you get down to where it's starting to flatten off, there's not really much point in using more and more cores. I mean, I suppose if you were on a system where you're not going to interfere with anybody else, maybe you don't care and you try and eke out that incremental gain of going from 8 to 12 cores. But particularly if you're on a system where you're sharing resources with somebody else, with other folks, you may want to stop here or here because you're going to be using up computational resources involved in all the communication, and there's just not a lot of point in doing that relative to the amount of speed up you're going to get. Yeah.
Are those diminishing returns a result of the fact that the computer can't partition the jobs equally, like in size, or is it because of overhead, or is it because of something else?
Yeah, I mean, all of those things are probably plausible, depending on what the problem is. If we've got, for example, the matrix algebra problem of multiplying matrices, and we're basically splitting up rows and columns, unless you get down to very, very many cores, you can probably split that up more or less equally into pieces as you increase the number of cores. But you're now starting to pass around, basically to do that, you probably have to pass the entire matrix to each of the cores. And then you're going to use only some of the rows or some of the columns to then multiply by that matrix. So for example, if you were doing the matrix multiplication, and maybe you split it up so you're going to multiply this block of columns by the entire matrix and this block of columns by the entire matrix and so forth. There might be smarter ways to do it, but if that were the computation, you still need to pass the entire matrix to each of the cores. As you increase the number of cores, that's just more time involved in the master sending each of those matrices to those cores. So that's some of the overhead in terms of just doing that communication. If you get a more complicated problem where you have to pass information from one of the cores, one of the tasks to another task, and as you get the data set split up smaller and smaller, you're probably having to do a lot more of that communication. So that would be another case where you would end that could cause this kind of decreasing returns to scale. But for other problems, your point is well taken that there may be cases where it gets hard to split things up equally. And so you might have 4 cores that finish really quickly, and then there's a laggard core that's doing more of the computation, and that's the bottleneck in terms of the computation. Other questions? Yeah, Jimmy?
So like, what is the kind of, do you have a rough calculation about like how many number of threads do you use so that like you can parallel increase your speed?
I think it's really pretty problem specific. That it's just you just need to try it and see how things are scaling. Yeah. I mean, my guess is that in many problems, once you get past say 8, you might not see as much of a speed up. But that, I mean, I think it really does depend on exactly what you're doing. Okay, so I said in words here what I also mentioned here in writing about testing the performance. Okay, so for the most part, we're going to mainly talk about problems that are very easy to split up into multiple pieces. Part of the reason is just that we only have so much time to spend on this particular unit. Another is that a lot of stuff can get done there are oftentimes in a given problem we can speed things up by just relying on splitting things up in a fairly naive way. So basically what an embarrassingly parallel problem is a problem where the computations are independent of each other and there doesn't really need to be any communication between the different pieces of the computation. So basically the only communication that needs to get done is the master needs to distribute the data to the separate processes. Those processes need to do their own thing. They don't need to communicate with each other. And then all they need to do is pass the result back to the master. So that would be an example of an embarrassingly parallel problem. I guess that's a description of an embarrassingly parallel problem. Some examples of embarrassingly parallel problems are if you're doing simulations, you're often doing independent replicates in a simulation, so you can just dispatch the replicates to different cores, have them do the computations and return the results. Bootstrapping is another example. Anytime you're doing a stratified analysis where you're breaking up your data set, that would be another example. And we could come up with others, but those are some of the situations where we can rely on doing things in an embarrassingly parallel sort of way. I will note that for a lot of these, we're going to rely on random number generation, and it's important to think carefully about making sure that the random numbers are independent from one task to another, and we're going to come back to that in the simulation unit where we talk about how random numbers are generated, so I'm going to skip over that for now. Okay, so this note about load balancing is basically the question that Alex brought up, which is basically, in some cases, and particularly in these embarrassingly parallel problems, we can basically take our computations and break them up essentially equally amongst our different tasks. And that's the ideal situation, because then hopefully there's not going to be any sort of bottleneck of one task being slower than the other tasks. But in other types of computations, that's not necessarily going to be the case, and we might have a computation where there are 3 different chunks that need to get done. They might even be able to get done independently, but one of them takes 3 times as long as the others. And in that case, there's some advantage in dispatching the 2 smaller tasks to their own processors, but we're still going to have the bottleneck being the one that takes the longer amount of time. So thinking about what your computation is and whether there's going to be a bottleneck in terms of how you break up your computations is something that's important to think about in those cases. So this question that I posed here in the notes, we basically already sort of discussed over the last few minutes about trade-offs between communication of passing information back and forth either between the master and the slaves or amongst the slaves themselves, versus some of the other things to think about are this question of bottlenecks and whether each of the tasks is actually taking more or less similar amount of time. I guess actually there are some more things to think about here. So maybe we should pause here and think about this a little bit more, about this question. So suppose I have a few very large tasks, and I am going to dispatch those. What would you see as the advantages of doing that as opposed to having many, many small tasks? Yeah, go ahead. That's a good point. It sort of depends on how we're distributing the original data. If we have to distribute all of the data to every task, then in that case, it would be an important point, that we would be basically duplicating the amount of memory we have on our master for each of the slave processes, and that might get to the point of running out of memory. In fact, it very easily could. If you have a 4 gigabyte job and you have a 16 gigabyte machine, that's fine. But if you have 8 cores and you make 8 jobs out of that, 8 times 4, 32, you're all of a sudden over the amount of memory that the machine has. So certainly memory use is something that we would want to think about in terms of and how that interacts with whether we have large or small tasks. We've already sort of touched on the point of if we have a few large tasks that we might not need to do, so we might use less memory, per your point. We might also need to have less communication, that if we do need to distribute all of the data to each of the tasks, then there's going to be less communication going on if we have a few tasks, we potentially, although not always, would have less communication. Other limitations or advantages that you can think of with many large tasks, with a small number of large tasks? Yeah, Alex.
You said about debugging?
Okay, so there's more. So I guess say more about what you mean by that.
It's easier to debug if you have fewer tasks. There's less chance that something will hang or there's some problem with communication.
Okay, yeah. So we may have less of an issue if we're running fewer tasks. There may just be sort of fewer that could hang or could have problems go wrong with them. And in that case, so it might be sort of more robust by having, so maybe a sort of less hanging potentially. Okay, what about having many small tasks? Any advantages to that you can think of? So I mean, one obvious one is just that you can only get to having, if we have 8 cores available on our machine, obviously we want to try and have at least 8 tasks being done. Otherwise, we're not going to take advantage of all of the cores on the machine. Anything else occur to people? Yeah.
You're saying advantages for small tasks now?
Yeah, we're sort of opening it up then.
Many small tasks, like if there's an error in a bug in one of them, like what effect it goes. You're still being fairly simple.
Yeah, I mean, oftentimes we're running the same code, but I suppose if we were doing like a stratified analysis, that might be one case where you might have something go wrong in one subset of the data and not in another set. So that would be one possibility. Anything else that occurs to people?
I mean, might be more
Okay, so one of this question of load balancing, of how do we balance the time? If we're breaking things up into large chunks, we might not. Yeah, I mean, I guess I'm not exactly sure how it would play out, but we would want to think about whether it's easier to get more or less equally sized chunks of calculation if we're breaking up into small versus large tasks. Another thing to think about on a larger system that's shared across multiple users is if you're dispatching a lot of small jobs, those are going to sort of fit together more easily with other people's jobs than if you have a lot of very large jobs. So suppose I have 3 jobs, each of them takes each of them takes a very, very long time. Then I might sort of tie up a whole computer for a day or 2 days. Whereas if I can break that up into thousands of small jobs and dispatch all of those jobs at the same time, the operating system or the scheduler may be able to sort of manage tasks and interleave them with other people's jobs. So it's sort of like passing sand through a funnel versus passing big rocks through a funnel. Everything's going to sort of move more smoothly if you have small tasks. So that sort of thing may come up in a system where you're sharing resources. And then I guess I'm not totally sure how this would play out exactly without having a particular example in mind, but we would want to think about, losing my train of thought. The question of whether any particular task would be a bottleneck, depending on whether it's a small number of large tasks or a large number of small tasks. So let's quit there, and we'll see some more examples of using R for parallelization next time.